Welcome to my video presentation for the 5th International Conference on Water Resources and Wetlands. Many thanks to the organizers for the invitation to present my work and having the foresight to ask for a video presentation in case the connection fails. I am USO and I am presenting from my garden in Nayarit, Mexico. I present my paper entitled Development, Economic Growth and Species Endangerment. As you will notice, it is early stage work, so I look forward to your comments and suggestions. Why care about biodiversity, some of you may ask. Ecosystems that are richer in biodiversity have been found to be more efficient and more stable. Biodiversity loss has been linked to higher rates of infectious disease. Biodiversity is thought to have large option value for the development of medicine, and many of us consider conservation important for species their intrinsic value. Yet, biodiversity is under threat around the world. The Intergovernmental Panel Science Policy Platform on Biodiversity and Ecosystem Services, in short IPBES, reported in 2019 that human activities have altered most ecosystems to the extent that a quarter of plant and animal life is pushed to the brink of extinction. Current levels of biodiversity loss are thought to be beyond safe planetary boundaries. The IPBES report lists the most important drivers of biodiversity loss as changes to land use, harvesting, climate change, other forms of pollution such as nitrogen pollution and invasive alien species. According to the Living Planet Index, freshwater bodies and wetlands are amongst the ecosystems that are worst affected, where global freshwater vertebrate populations have declined to just a third over the past 50 years. While there is little debate over these direct drivers of biodiversity loss, the influences of economic growth and GDP per capita on biodiversity loss are more debated. The debate seems to revolve most prominently around the environmental Kuznets curve hypothesis, which predicts that pollution first rises with economic growth, but that once some turning point income level is reached, that further growth will lead to environmental improvements. My reading of this environmental Kuznets curve literature is that there is some evidence in line with the hypothesis for local air pollutants such as sulfur oxides and particulate matter pollution. However, that in general the environmental Kuznets curve hypothesis seems to be rooted mostly in wishful thinking. For example, in a meta-analysis of over 500 estimates for some 70 different studies focusing on deforestation, Schumert et al. Find that the more recent the year of publication, the more the likelihood of having an environmental Kuznets curve declines. In my 2019 publication in Ecological Economics, I had used ordinary least square regression analysis to explore the association between species endangerment using IUCN and red list data and regional GDP per capita. I found species endangerment increase with GDP per capita after controlling for some regional observable characteristics, and I found no evidence of an environmental Kuznets curve. The paper that I present here builds on this work that I've published in 2019. Let me briefly explain how I used IUCN and red list data to express IUCN assessments in expected extinction rates. Several species assessment categories, such as vulnerable, endangered, and critically endangered, come with a probability of extinction within the next decade or century, depending on the category. I wish to express these assessments in expected extinctions relative to background extinction to make them more comparable to each other and to studies on planetary boundaries. For background extinction, I took the upper bound estimate of one extinction per million species years from Rockström et al. The planetary boundary, as expressed by the same authors, is set at 10, and later Stefan et al. Added a zone of uncertainty up to 100. The map shows that slightly half of global landmass and all oceans face expected extinction rates that exceed the planetary boundary beyond uncertainty. You can also think of the map as showing some weighted average of IUCN assessments where critically endangered and endangered species receive higher weights. The map illustrates that one finds the highest expected extinction rates in tropical regions and on islands. My map also suffers from a form of map distortion due to the double counting of species with large ranges. Species with large ranges are also less often endangered, and therefore the average regional extinction rate is 190 times the background rate, while the global extinction rate is about 750 times this background rate, under the assumptions spelled out in the paper. The work that I present today is inspired by this map distortion. Instead of organizing my data by region, I chose to organize data on the species level and focus on a set of relatively short-range species that are endemic to only one region. For this paper, I decided to organize my data on the species level. I inspected nearly 10% of the 2019 IUCN Red List and chose to include in my sample only small range species that are endemic to one of the regions as indicated by the IUCN. For these endemic species, I created two dummy variables, threatened and decreasing. Threatened was available for 3,500 observations and takes 1 for the categories vulnerable, endangered and critically endangered, and 0 for species that are near threatened and of least concern. Decreasing equals 1 for species with a decreasing population trend and 0 otherwise. Subsequently, I matched the species assessment variables to regional GDP data and other controls used in SOL 2019. My sample of short-range species consists of mammals and plants, where I inspected all mammals in the IUCN population except for the order of rodents, and all plants except for the Magnoliopsida class. My sample of endemic species is more endangered than the IUCN population. For example, 70% of plants in my sample are endangered as compared to 40% in the IUCN population. I chose to focus on endemic species to prevent this issue of double counting, and arguably the analysis over the subsample of endemic species is less sensitive to regional spillovers. Similarly, one could argue that my sample consists of a set of species that are most sensitive to regional policies. However, it is also good to keep in mind that my sample restriction leads to certain taxonomic groups being better represented in my sample than others. Moreover, my sample restriction criterion is sensitive to the regional division of the IUCN. As you can see, it led to a high concentration of observation from a few regions. Possibly, you may wonder why, for example, Borneo is missing from this top 10. And this is because the IUCN data considers Kalimantan, Sabah, Sarawak, and Brunei Darussalam as separate geographic regions. There are species from 263 regions in my sample, yet half of the observation comes from these top 10 regions. The results that I show are robust to excluding these 10 regions from the analysis. Here I show the results from an OLS regression. Based on the analysis with small range species, species endangerment decreases with GDP per capita, and endemic species, their populations show fewer decreasing trends with higher GDP per capita. As GDP per capita is highly skewed, I had taken the natural logarithm first, which means that the doubling of GDP per capita is associated with about 5% less endangered species and about 8% less species with decreasing population trends. The results are qualitatively the same for probit and logit regressions. You may have noticed that the results show the opposite relation between species endangerment and regional GDP per capita as compared to SOL 2019. The association with human population density remains unchanged between the two papers. More densely populated areas are associated with more species endangerment. My best explanation so far for this paradoxical finding of the opposite associations with GDP is that the association with GDP is estimated over a rather different part of the income distribution. The histogram shows that the endemic sample contains more observations from low-income regions. In conclusion, here I have analyzed a subsample of small-ranged mammals and plants that suggest species endangerment decreases with income. In 2019, I found the opposite association for largely the same IUCN data, but organized by region, which resulted in a considerably richer sample. Together, these findings suggest a relation that is entirely opposite to the environmental Kuznets curve, namely one of decreasing impact on biodiversity at the first stage of economic development, followed by increasing species endangerment once some threshold income has been reached. My findings suggest that poverty is more harmful to biodiversity than affluence. I aim to check the robustness of my findings and explore possible mechanisms by adding variables on agriculture, education, poverty, and trade.
I'd like to close with backing the call by Hickel et al. And Otero et al. To include post-growth scenarios in future international policy documents. These are the references that I used on my slides in full. Pause if you want to read all.
This is what I prepared for today. I'm happy to share the slides or working paper in case you would like to go over some details. And I look forward to hearing your alternative explanations or suggestions. Thank you for your attention.